Okay, so in this lecture, we are going to look at effects in FStar. As I had previously mentioned, FStar is an effectful language. This is unlike OCaml, which is unlike Coq, which is a purely functional language. And it is very similar to OCaml that it allows lots of effects to be done, including allocating memory, modifying references, throwing exceptions, non-termination, and so on. So in this lecture, we are going to see effects, and particular, we are only going to look at effects that have to do with heaps, right? What do I mean by heaps? Heaps are generally what you do with references, right? You can create new references, you can alias them, you can read and write to references, and you can mutate the references, and this would be an effect in FStar. So let's look at how we can program, but also automatically verify programs that use effects. So I've opened a bunch of modules. The details are unnecessary. So here is a function that's an effectful increment function, right? So in FStar, we have references. These references are similar to references in OCaml, right? So refz is a reference to a location on the heap that holds an integer, and the increment function takes that reference and then updates the reference such that the value in the reference is the old value plus one. So just to remind people who don't know OCaml, so colon equals here. It doesn't quite appear nicely, but colon equals here is the assignment, assignment to reference, right? And bang is a unary operator that retrieves the value that is contained in the reference, right? And the computation itself does not return anything. It just updates the reference. So the result is a unit. And this is a computation type, right? So it has some effects. In particular, it has the ST effect. ST effect is short for state, essentially. And state is sort of encapsulating the things that you can do with references. Okay. And this capital S small t, some type, is actually a syntactic sugar for this type here. This is a computation type, right? This is a refined computation type, which says that name of the effect is ST. The computation itself returns a value of type A, right? And there's a pre and post condition. And the pre and post conditions are quite interesting here, right? So, okay. So requires is the precondition. It is a function that takes the heap before the execution of this computation, and it is some proposition, but in the simple form STA, the condition is just true. And similarly, the post condition takes three arguments, right? It takes the pre-heap, essentially the heap that was there before the execution of this computation, the value that is returned by the computation. So this V is a value that has type A, right? That's the value returned by the computation, and the post heap. Post heap is the heap that is left at the end of the computation. And in the simple form, the proposition is just true, but you can make it more complicated. Again, just to repeat, H3 is the heap before the computation. H post is the final heap, right? And the post condition takes both the initial and the final heap. And V is the result of the computation. V is of type A. So we gave a very weak specification for increment here, right? We just said increment is a function that returns unit. So you could have done this in OCaml. And this is the similar type that you will have in OCaml, except that you wouldn't have the ST, right? So this would just be unit, because OCaml does not track effects. FStar tracks effects, but also gives you a way to refine what the pre and post condition should be. So we can make the post condition very specific. So have a look at increment 2 here. Increment 2 is a function that takes a reference R, right? And it's an ST such that the computation returns a unit, right? It just returns a unit value. There is no precondition, so we just ignore the fact that there is a preheap. But in the target heap, in the final heap, we say something very specific, right? We say that Recall that this is the initial heap and this is the final heap. Informally reading the specification, it says that in the final heap, there is a location R which is modified, right? Between the initial and the final heap, the only location that is modified is R, and this R is this R, right? Which is passed as an argument to the reference. And the cell, you have to sort of read it as the value of the reference R in the final heap, H2, is the same as the value of the reference R in the initial heap plus 1. Okay, so there are two new constructs here, right? It says one is modifies, which captures what locations are modified between the initial and the final heap. The only location modified is R. In particular, modifies also says no other location is modified, right? Anything that is not mentioned here is not modified. And it also says, cell here says that what is the value of this reference in this heap, right? It just retrieves that value. And cell says that the value of the reference in the final heap is the same as the value of the reference in the initial heap plus 1. Because that's what increment does, right? So it takes the reference R and it modifies the reference, and the value in the final heap is 1 plus the value in the initial heap, right? Which is what is captured here. So there is a lot of new syntax and terminology here, but in fact, we can break this down. So in order to reason about ST effect, FStar provides two modules. One is called heap, another is ST, right? Heap is a module that is used for specifying properties on the ST effect, right? This modifies and the cell are functions from the heap module, and ST module is used for programming with references. So this will contain what? This will contain the assignment function, right? And this bang function, right? Which takes a reference and retrieves the value. So let's first look at what the module heap is. I should say that the specifications here are very simple. We will refine it as we go along, but I'm not providing the entire specification here. I'm only providing what is relevant. Okay. So in the module heap, we have an abstract type called heap. We don't know what that heap type is. It's just an abstract type. Heap only is useful for verification, right? We don't actually use that to program against. So it is okay if it is abstract. The heap variables here only appear in the specification, right? They don't ever appear in the computationally relevant parts. The computationally relevant parts, I mean, not specification. Okay, so that's heap. And reference is a type constructor. Essentially, reference takes a type and returns you a new type that is a reference. So you can have a ref of int, ref of bool, ref of string, or whatnot, right? And cell is a function. SCL cell is a function. It's select, which operates on any type, right? It takes implicit type parameter A. That is why we don't explicitly have it here. It takes a heap. It takes a reference of type A, right? A comes from here. And then it is a total computation that just gets the value of A, right? And another thing that is new here is this gtot. This is not important. I'm just mentioning it because it appears here. Just think of it like total computations, but those computations which only appear in specifications, in the pre and post conditions. They don't actually appear anywhere for computationally relevant parts, and that is why we specifically have a special effect called gtot. So read the G as ghost, and this term ghost is typically used in programming languages for specifying things which are not computationally relevant, which is only used for verification. And gtot is the effect that specifies a total function in a computationally irrelevant fashion. Okay, so I'm not going to refer to gtot ever again. It is just I just explained it because it is not something that we've seen before. Okay, just to recall, cell gives you the value of the reference in the heap, and the value is of type A, right? So when you give a ref A, the value that you get is type A, value of type A, right? And we have one more sorry, we have one more function here called address of, which takes an implicit type A, right, and takes a reference and then returns you a natural number. I mean, this seems quite odd, right? What is it that we are returning, taking a reference? You can sort of think about the heap as an abstract heap for the verification purposes, just like what we had used in Coq, right? So where we mapped the heap as a map that goes from integer to integer. But here, the heap is a map that goes from the key is an integer, right? The value is an arbitrary type value, right? It can be a string or a bool or whatnot. In particular, it is of type A here, right? These A could be different for different indices. The only constraint that we have is if for a particular natural number, if I pick the location 0, then I cannot have two references there, one of which is a type bool and another which say is a type integer, right? That just break type safety. So that is an axiom that is on the side that is not described here. But address of, you can sort of think about that as just casting the pointer type in C to an integer, right? It just gives you some integer, which is unique. And that is precisely what we are using here. Actually, to be fair, we are not going to manifest this integer explicitly. This is only used for verification purposes, right? That is quite important. And that is the reason why this is part of the GTOT effect, this ghost total effect. Okay. And modifies itself is just a function. The modifies is a function that takes a set of natural numbers, right? The syntax is sort of getting the address of the reference that is mentioned here, right? So it takes a set of natural numbers, a set of heap locations, right? It takes the initial heap and takes the final heap. And what does the specification say? For all type A and references of type A, for all location address of R such that they are not, this tilde symbol is not. So for all addressees that are not part of S, selection of H1 of R, the value of R in H1 is the same as the value of R in H0. So the way to informally read this is, for all the locations that are not explicitly present here, right, modify says that for those locations that are not part of this set, the value of those locations in the initial heap is the same as the value of the locations in the final heap. Again, this tilde is a negation, right? We sort of say for all locations that are not part of the addresses here in the set, the value of that particular location remains same between the initial and the final heap. So modifies is just a function that uses this address of helper function. Okay. So this has to do with specification. What about actually programming? So these have similar types to what you will find in OCaml, but they have richer types, right? So that's the intuition here. So exclamation that we used here operates on a reference, right? It operates on, it takes some type, which is an implicit type, operates on a reference of type A, and then returns you a value A in the ST computation, right? In the ST effect. And this is the type that you will have in OCaml, right? You'll just say, oh, exclamation takes a reference A and returns A. But there is something interesting going on in FStar where we have a particular postcondition. In particular, we say that the precondition is nothing, but the postcondition is such that the value that is returned by dereferencing, let's call it X, right, is the value that R has in the initial heap, right? If you read R in the initial heap, then it should be X, and that is the value that is returned by this computation, right? It sort of explicitly lays out what the semantics of the exclamation should be, right? And importantly, exclamation does not modify the heap, right? It only reads it. So between the initial and the final heap, there are no modifications. Okay, so that is the specification of what dereferencing a reference in the heap means. So what is assignment? You can sort of work it out now, right? So assignment takes an implicit type, takes a reference, takes a value, and it does not return anything, except when it has an effect. What effect does it have? The precondition is nothing. The postcondition says that um, it modifies the location R in uh, okay, so the other actual way to read this is between the initial and the final heap, the only location modified is R, right? That is what the modified clause says. And what it says is if you read R in the final heap H1, then that will be the same as the value that you assigned to this location. Where does V come from? V comes from here. Okay, so the value of R in the final heap is V. And that is the value you actually assigned to this reference. And that's the specification of what assignment should do, right? Okay, with that, with those specifications, now we can actually see how the verification goes through, right? So I've rewritten increment using let syntax here, just to make it clear that the verification is compositional. So in particular, this particular statement has single effect, which is reading the reference, and this particular expression has a single effect, which is writing to the reference. So intuitively, you can say that um, the the specification for this one says that you start from some initial heap, right? And the precondition is nothing on that initial heap. You are left with some final heap H2, right? And for the first step, you just read the value, right? So there must exist a intermediate heap and a value that you read, X, such that between these two heaps, H0 and H1, which is the result of reading this reference, nothing changes because read doesn't change. This is exactly the specification of this one, right? And X is the value of reading R from H0, right? That is the initial heap. You are left with H1 now, and you basically thread that heap through, right? You take that heap, you consider that as a value, you feed it through to the rest of the program. And for the rest of the program, the specification is the next step is going to do actual modification, right? It takes an R and it's actually going to update that with X plus 1. So between H1, this intermediate heap, and the final heap, R location is modified, right? And if you read R in H2, then it is X plus 1. And the X is coming from this existential variable here, right? And I mean, you can basically simplify this to the original specification that we gave, right? So you can basically throw away this intermediate there exists clause. How can we throw it away? So we can, what we had written is between H0 and H2, R is modified. We're talking about the intermediate heap here, right? And if you read the value of R in the final heap, then it must be 1 plus the value of R in the initial heap. So how did we come about this? This is just logical reduction, right? The first thing is we have an axiom in FStar which says that modification is transitive, right? Um, what does this axiom say? Let's take two modified sets. The first one captures the set of locations modified between heaps 0 and 1, right? We take three heaps, right? 0, 1, 2. The first set captures the set of locations modified between 0 and 1. The second one captures the set of locations modified between 1 and 2, 1 and 2. So the lemma says that if the S01 captures the set of locations modified between 0 and 1, and S12 captures the set of locations modified between 1 and 2, then it must be the case that between H0 and H2, the set of locations modified is the union of the sets of 1 and 2, S01 and S12. That sounds trivial, right? But adding this axiom is quite useful because now you can sort of take these two propositions, right? These two propositions, this one, and actually construct this one. Thanks to this modification is transitive property, you can take these two individual modifies properties. Because these two are the same, you can combine them together by set union on this. And the unioning empty set with R will give you a singleton set with R. And that is precisely what is going on. Okay, and for this case, you just replace it by rewriting, right? So here is X, here is X, just rewrite it here. And now you can simplify it, right? So you just replace X with the cell H0R, cell H0R here, you will get this condition. And all of this can be, once you have this transitivity property, the rest of the fact that these two are the same can be automatically discharged through the SMT solver. The SMT solver is very good at doing these sort of reductions, right? And that is why both of these seem to satisfy the specification, right? Both of these are valid specifications. But it has to be the case that from these basic axioms, right? The basic axioms that I've given here for bang and colon equals, FStar needs to construct a pre and post condition for the combined program that combines the program through lead binding, right? These one give you specification pre and post conditions for individual operations, the read and write, but FStar has to somehow infer the pre and post condition for this entire program and then check that that particular both pre and post conditions inferred are strong enough such that whatever post condition that you have here is implied, right? So you cannot, you have to sort of get that pre and post conditions. FStar has to construct this and then say, now check whether this is a subtype of this pre and post condition, right? And how does FStar does it? FStar does it in a very similar fashion to what we saw in Hore logic, right? The idea here is FStar has support for weakest precondition inference. And the term is particularly not interesting now, but the intuition here is that just like how we define syntax directed rules for composing together the Hore logic triples in the Coq lecture, right? We had a rule for sequencing. It said if you want to talk about sequencing, there must be an intermediate state where you can step through, right? We're going to do the same thing here, but for let. The notion, the notion of sequencing here is through let, and semicolon is just a syntactic sugar for let unit equals E1 in E2, right? That will be equivalent to E1 semicolon E2. So given individual specifications, you have a way of composing them together. And that is what FStar is doing, and actually inferring the intermediate specifications automatically. So how does it actually work? Let's consider the term let x1 equals z1 in E2. Okay, so this is what we are going to infer the specification for. Let's say that under some gamma, E1 has the type st, it returns a value of type T1, right? And has some precondition on the initial heap H0, right? Some precondition. I'm not going to qualify this precondition, it's just some precondition. And as a post condition, it's going to return some x1, right? This x1 is matching this x1, right? When you evaluate E1, you get an x1, and that is the x1 here. And you also get a new heap, right? And some post condition is going to hold on the heap. The observation here is this is sequencing, right? If I do x1 equals E1 in E2, whatever the post condition of E1 is, that has to be the precondition of E2. And that is what we are using here. Now we extend the gamma G, the environment, with x1, the variable x1 has type T1, right? And we are going to check that E2 has also an ST effect, returns a value of type T2, right? And for the precondition, we are going to construct that from the post condition that is specified here, right? It takes some heap, right? Pre-heap, H1, right? This H1 is the same as the H1 here. The target heap here, H1, which refers to some variable H1 here, is going to be the same here. We use the same variable here. And there exists some H0, right? We don't know what that precondition is, but we know there exists a precondition H0. right? This postcondition may refer to this precondition. So there will be an existential precondition here, right? This is the heap that existed before this let started executing, right? And this postcondition can refer to what? Refer to this initial heap, refer to the heap that occurs as a result of evaluating U1 and also X1. So H1 is in scope, H0 is in scope because of this exist clause, and X1 is in scope, right? And it ensures that, uh, excuse me. So, and it ensures that you have a heap H1, which is the initial heap for E2, right? And it is going to give you a value X2, and the final heap is H2, and some post-condition prime holes. So if you can show that, you can show this condition about E1 and this about E2, then you can automatically infer that let x1 equals e1 in E2 has the type, right? It is going to return value of type T2, which is the same as the value returned by E2, because that's the semantics of let, right? And the precondition for this is the precondition of the entire thing, which is the precondition of E1, right? So you take this precondition, you plug it in here. What about the post conditions? The post conditions will have to satisfy both the post condition of this intermediate step and the post condition of this uh, E2, right? So it has to satisfy both E1's post condition and E2's post condition post prime. So the way we represent that is, we are going to get some heap, which is the initial heap, which matches H0. We are going to get some final heap, right? Some final value. In order to reify this intermediate step, we use an existential quantifier here, right? There exists an H1, X1, H1, such that this post condition can refer to those. And this post condition, um, the post conditions that you require are a conjunction of both the post conditions of E1 and E2, right? This is how FStar actually constructs the specification, infers the specification for um, this particular, when you just write this program, right? Increment 4 r equals let x bang r in or assign x plus 1. It's going to do this internally and then come up with the specification that is strong enough to verify whatever type ascription that you give, right? So it has to infer the weakest precondition and the strongest postcondition, so that the precondition, whatever precondition that you choose here, will imply that precondition, and the whatever postcondition that is inferred here will imply the postcondition that is specified here. Okay, so this is what goes on internally. There's a lot going on, but the point here is all of this is sort of meta, right? When you program, we are not actually using anything. We just write the specification and the things go through. And that's the power of this compositional reasoning that FStar offers. Okay, so now let's actually step through and look at how this proof is applied by FStar. So it first looks at this let, right? I'm going to read this reference and then I'm going to assign x plus 1 to it. First, I'm going to look at this read. From the specification that is attached to reading a reference, I know that there exists a h1x, which is the result of reading, right? Between h0 and h1, nothing is modified. H0 is the initial heap. And if you read, sorry, this need be, if you read R in H0, then the value is X, right? And for assignment, it goes and consults the assignment specification. The assignment specification says that the only thing that is modified between this H1, that is the result of evaluating this let, and H2 is that we modify R, right? And if you read the value of R in H2, that'll be X plus 1, because X plus 1 is what we have here. So how does the specification here come from these two conditions? This is what FStar has actually computed based on this particular let rule and the specification attached to reading a reference and writing to a reference. So this particular property comes directly from transitivity of modifies, right? So transitivity of modifies implies based on this property and this property, we know that this holds because modifies is transitive. And here um, you replace this term, right, for x here, and this property will naturally follow. So that is how FStar is verifying that this program has this type. Essentially, it's doing type checking. It's inferring the types for this term, like this whole term, and then checking whether the specification here holds by subsumption, by subtyping. Okay, so we've done increment. Now let's do something a little bit more interesting. So we are going to implement swap. So given to reference, swap is going to swap the values of the reference. So this is quite simple, right? So what you do is you save the intermediate value in T. You update R1 to the value of R2, right? And R2 is the saved value T. So we know that this swaps the values that are contained in R1 and R2, right? But now in FStar, we can actually write a specification that captures that the swap happens. So how do you write it out? Swap takes two references, R1 and R2, both of which are references which contain integers. It is an ST effect, right? It does not return anything useful. So unit, there is no precondition, right? And in the post condition, we have the initial heap and the final heap. In between the initial and the final heaps, right? The locations R1 and R2 are modified because swap is going to modify them. And if you read R2 in the final heap, then it will be the same as R1 in the initial heap. And if you read R1 in the final heap, that will be the same as R2 in the initial heap. So there should be no surprises here, right? Let's see how FStar actually verifies this. So just by applying the rules, right? From dereferencing rule, we know that there exists a H1 T, right? These are existential variables because they are not explicitly mentioned here. Nothing is modified between 0 and H1, H0 and H1. And the value of R1 is reference that you read in the initial heap is T, right? And let's call that P1. And what about the assignment? So here between H1 and H2, R1 is modified. And the value of R1 in the final heap is the same as the value of R2 in the initial heap, right? So we read the value of R2 in the initial heap and save it to the value of R1 in the final heap. And finally, what we do between H2 and the final heap H3, which we actually mentioned here, right? R2 is modified and read the value of R2 in H3, then it is going to be T. So now we have these three conditions. We have to prove this, right? Now, this modifies property directly comes from the transitivity rule, right? So you have H1 here, H2 here. So you can take the union of all three, which is R1, R2, and H0, H3, right? So which is the same as this one. So it says that between H0 and H3, R1 and R2 are modified. And we have two more properties to prove. The first one we have to prove is we have to prove that select of H3 of R2 equals select of H0 or R1. This directly follows from P1 and P2, right? If you rewrite T, in this case, we have select of H3 of R2, select of H3 of R2, double equals select of H0 of R1, select of H0 of R1. That directly follows. We have one more rule here, right? We have to show that select of H3 R1 double equals select of H0 R2. So how do we do that? From P2, right? P2, we know that select of H2 of R1 equals select of H1 of R2, right? Let's call that A. And we know that from P1, between H0 and H1, no location is modified, right? So if I have select of h1 of R2, because I know h1 and h0 don't modify anything, I can replace h1 with h0, right? It doesn't modify anything. So it must be the same as replacing h1 with h0. Let's call that P. And finally, P3 says that between h2 and h3, only R2 is modified, right? R2 is modified. So if I take cell h2 R1, right? This is not R2, right? I'm choosing R1. I can certainly replace that with H3 because between H3 and H2, only R2 is modified. So it does not modify R1. So I'm going to change the heaps here. I'm going to change it from H2 to H3. So we have ABC now. By transitivity from ABC, we can prove cell H3R1 double equals cell H0R2. How do we do that? Search for cell H3R1. We have cell H3R1. We have cell H2R1 here. We have cell H2R1 here, which is equal to cell H1R2, which is equal to cell H1R2, which is equal to cell H0R2, which is the term cell H0R2 that we need to prove, right? Just through the transitivity of equality and cleverly using the modifies function, we are able to prove it. And all of this is automatically done by the SMT solver that is sitting underneath. So that is how the SMT solver actually proves that the swap function has the intuitive specification that we expect that to have. Okay. So a particular thing to note here is the variant is correct even when R1 and R2 are referring to the same location, right? Even if R1, consider these as pointers, right? Pointers to the same memory location, then this operation is not going to change the value of the location, right? They will leave the value as they are. So I don't know if you've seen this funny way to do swap using additions, right? So take R1 and R2. This doesn't use a temporary. This just sets R1 equals R1 plus R2. Now R1 contains the sum of both, right? So from the sum, subtract the value of R2, you will be left with R1, right? From the sum of R1 plus R2, subtract R2, you will get R1. So this clever combination of addition and subtraction actually swaps the values. Yeah, I don't know whether you've seen this before. This is quite standard. This is like the standard interview question, like the startup interview question where they will ask, "Oh, can you swap variables without using a temporary variable?" Right. This is one you can also do one based on bitwise operations. But the important thing to note here is this particular specification only works if R1 and R2 are not aliases and addition does not overflow, right? If addition actually overflows here, then you are going to get strange values. So the correctness of this invariant relies on R1 and R2 not being aliased and int being a mathematical integer. So the integer that is used in FStar is actually a infinite precision integer, right? It's infinite bit integer. So this is not like 34 bit or 32 bit or 64 bit. It extends to plus infinity there and minus infinity here, right? And that this property is satisfied. In order to state that R1 and R2 are not aliases, we add a precondition. We add a precondition to this function which says that in the initial heap, right, the address of R1 is not equal to the address of R2. We type not equal to by greater than less than, right? Less than greater than, that becomes not equal to. We are essentially saying that R1 and R2 don't point to the same memory location, right? Once you do that, the rest of the proof stays the same. The proof actually, you don't have to do anything more interesting. FStar does all the work for you and proves the program for you. What I would recommend is you actually sketch the proof by hand and convince yourself that, like the same way we did for the earlier example, right? Convince yourself that the proof actually works. Okay, so that's that. That is all about swap. And the next example that I want to show is a series of recursive functions that perform some additions, right? The first one we are going to see is we are going to use the reference to count from 1 to n. We are just going to given a input n, count st, given a number n, just adds so many numbers. So adds 1 plus 1 plus 1 plus 1 plus 1 n times. So the result has to be n, right? So, but we are going to use a reference for that, intermediate reference for that, right? Our program is going to, let's ignore the type for now. Let's just look at the program. So we are going to create a reference. We initialize that to 0, right? So we alloc a reference, initialize that to 0, and we call this helper function count st prime with the reference and n. Whenever n is greater than 0, I am going to increment this reference, right? R equals r plus 1, and tail call with the same r and n minus 1. And finally, what I do, I just return the value that is contained in this reference, right? So what is the specification that I can, let's look at the specification here, right? So count st prime takes a reference, takes a n, which is also a natural number. It is a st computation that returns unit because it is not going to return anything interesting. There is no precondition, and the postcondition says that if you start at some point, right? I I I say that the value of r in the final heap is n plus the value of r in the initial heap, right? So this is like a this is a loop invariant, right? So whatever the value of r is, you can't say r is 0 here because it needs to hold for the recursive call as well. But what this says is if you start with r as some value in the initial heap, right? When the when the function terminates, the value in the final heap is going to be n plus the initial value of r in the initial heap, right? And it modifies r. So between h0 and h1, the location that changes is r. Okay, so this should be fairly straightforward. So what is the specification for count st now? So count st, there is no precondition. For the post condition, we take h0, h1, x. The final result that is returned is just the dereference of r, right? So whatever n that you give should be the same as the x here. So we say x equals n, and we add this property, right? So we say there is nothing that is modified between h0 and h1, the input heap and the output heap. If you are following this very closely, this would be very strange because we have this new reference that we did modify, right? Our specification even says it modifies. So why is it that we can say that modifies nothing between h0 and h1? When I originally introduced the specification for modification, I was sort of ignoring certain facts. In particular, I was ignoring the fact that there could be new allocations. The real specification for modifies is here. So we introduce a function called contains, which essentially is a set membership thing, right? So it says given a type, given a heap, given a reference, it returns you some type 0. Think of type 0 as a proposition, which holds if the reference is in this heap, right? It's a membership check, whether this reference is part of this heap. The actual specification for modifies says that ignore the pattern thing for now. I'm not going to explain this pattern. The specification for modify says that takes a set of locations. Again, ignore this f star t set. It's a set of natural numbers, right? And an input heap and an output heap. And it says that for all locations that are not in the set mentioned here, and H0 contains R, right? For only those locations which are actually present in H0, the value of H0 remains the same. In particular, what this says is if I add a new locations to H1, I don't say anything about this in the modified specification. So this specification here does not constrain H1 from having new locations that are modified. It only says that this specification says that whatever locations are in H0 are remain the same in H1, right? There could be new locations which I don't talk anything about. In particular, I allocated a new location here, right? Which I am going to modify, but this particular specification is sort of abstracting away the detail. It is only talking about those locations which are actually in H0. Okay. Okay. And what is the specification for alloc? Alloc takes a type, right? Takes an initial value, like the value here, and it's going to return a reference for you of the same type. And this is also an ST monad. There is no precondition, right? Precondition is simply true. What is the postcondition? The postcondition says, take the initial heap, take the final heap. I'm going to return you a new reference R. The modifies clause stays the same, right? Because I'm not modifying anything. I'm just adding a new location in H1. So modify is nothing between H0 and H1. In the final heap, if you look up R, the new location, then its value is the initial value that you supplied. And in particular, I say that H0 does not contain R, right? Because it's a new location, and H1 contains R. Again, this tilde symbol here is negation. Okay, so that's the specification for alloc. So now you can do more things, right? So just like we did counting ones up to n, you can count the numbers. We know that the sum of the first natural numbers is n times n plus 1 divided by 2, right? I use that as a specification. The rest of the program is almost the same, right? What we are going to say here is rather than the final value being n, the final value here is going to be the total from 1 to n, right? Sum total n. Okay, so this will go through, right? And the specification here is just saying the result that is obtained some state takes an n and then computes the sum of natural numbers from 1 to n. So the result is going to be sum of natural numbers from 1 to n, and it does not modify anything. This is a new allocation, and recall that modifies is only talking about the locations that are in H0. So this one goes through. Okay. Next, let's look at Fibonacci. We keep coming back to Fibonacci because I mean, it's quite small and it's interesting enough to express interesting constraints, right? So this is the usual imperative Fibonacci, right? What you do is you have two variables, R1 and R2, and for every iteration, what you do is you copy R2 to R1, right? R2 to R1 through the temp variable, and you say R2 is actually R1 plus R2, sum of R1 plus R2. So this is essentially going to start from some 1, 1, right? 1, 1. R1 will be 1, R2 will be 1. In the next iteration, R1 will be 1, R2 will be 2. In the next iteration, R1 will be 2, R2 will be 3, and so on up to n. So that is what we are going to do. So our Fibonacci specification is just the natural Fibonacci specification expressed as a recursive function, right? Two recursive calls. I'm going to write a Fibonacci ST, right, which takes a n and computes the nth Fibonacci number. It is going to return a natural number, right? No precondition. And the post condition is that the value return is the nth Fibonacci number. Again, this Fibonacci refers to the function here, right? The functional specification of what Fibonacci is. Between the initial and the final heap, it is not going to modify anything. We are going to use two locations here, right? And we are actually going to modify it, but the specification does not mention it. So we initialize R1 to 1, R2 to 1, and we call this recursive function, which takes the position as 1 up to n. So you can think of this as a for loop, right? Fibonacci ST prime is a sorry is a function that goes from I to n. So I has to be n has to be greater than or equal to I, right? That's a specification that you can actually assert here, right? R1 and R2 are references, right? And again, this specification is very similar to what you had done in the midterm and problem set 10, right? Where we know that at every instance, R1 and R2 are going to refer to Fibonacci numbers, right? Successive Fibonacci numbers. In particular, if you look at R1 in H0, it's going to be Fibonacci of I minus 1, and R2 of H0 is going to be Fibonacci of I, right? And this algorithm only works if R1 and R2 are not aliases. Otherwise, everything will break down. So that we also assert that one. And when this program actually terminates, what we have is we have a post condition which says that at the end of the program, in the heap H1, right? If you look at R2, that will contain the Fibonacci of n, that computes the Fibonacci of nth Fibonacci number. R1 will have n minus 1th Fibonacci number, right? And between H0 and H1, R1 and R2 are modified. And the algorithm itself is very simple, right? So it's I less than n, then copy the temp variable, compute the sum and store it in R2, and R2 becomes R1 here. And then you recursively call Fibonacci ST prime with I plus 1 for the next iteration, n R1, R2. Tail recursive Fibonacci to compute the rest of the computations. So the specification says that at the end of the computation, R2 will have Fibonacci of n, and then you just read the value of R2 and return it, right? And that will be X. And our specification says that that is going to be the same as Fibonacci of n. And because we've set it up so nicely, this just flows through, right? And what we've done here is we've proved the Fibonacci function written in an imperative way, right? We've actually written it imperative way, and the specification is not too complicated, right? So this is what you would have done if you had done a tail recursive Fibonacci, right? These two specifications are essentially what we had for tail recursive Fibonacci. And without much trouble, FStar lets us verify efficient state-based implementation of Fibonacci and verify it against the implementation of Fibonacci written functionally, right? So I hope that this has given some taste for how to program with state effect in FStar. In the further lecture, we'll see more effects in FStar. I'll stop here.